So good morning, everybody. Today we're going to have Alberto Montes will talk about this paper called Temporal Action Localization in Untrimmed Videos via Multi-Stage CNNs. That's a paper from Columbia University, and it will be presented in the next CPR 2016. So Alberto, thank you for preparing this talk, and the floor is yours.
Okay, so this paper we're trying to present is a framework to solve what I have been working on is on the detection part. So try to localize actions in videos from untrimmed videos. So well, here you can find the paper and the code if you want. So let's start. All the previous work related to videos, what they have been proposed is trying to extract features from frames using 2D convolutions, also IDT, improved dense trajectory, also feature vectors. And that's until now what are most of the papers related to videos what they have presented. They propose a framework called segment CNN. This framework has 3 stages. On the first one, they take a video which is untrimmed, so there are some temporal locations where there is background. In other ones, there are an action and then also more background. This is an example, and they make multi-scale segment generation. So they trim in windows and in different size windows, and then put them on the next stage. The next stage is take this segment and put it on the 3D convolutional network, or the one we have been talking a lot previously. Well, I have been working on it, and they build 3 models. The first one is a proposal network, which is the same as the 3D convolutional network, but at the last layer there are only 2 neurons, which are trying to say that whether it's action or it's background. So it's a way to pre-select all the segments if they need to be classified to be further classified. The second network is a classification one, which at the last layer has a classification with all the activities available, and the last one is a localization one. The localization one is the same as the classification, but they add a new loss function to try to improve the results and get the segments which have more overlap with the true annotation on the video. So that's the main goal of this segment CNN they propose. And also, after all, they add some post-processing to remove the less meaning segments and so on. So, well, that's program definition. The video is made up to a lot of frames, well, a variable number of frames. There are some annotation, which each annotation has the activity category and also the start and ending frames. And each video may have more than one annotation on it. On the first stage, what they do on the raw data of the dataset, they resize the image to the resolution, which is the input resolution from the 3D convolutional network. They also make windows of 16, 30, 32, 64, 128, 256, and 512 frames, and then they uniformly sampling to 60 frames, because the 3D convolutional network, the input is has this pixel resolution and also 60 frames of temporal depth as input. So they uniformly sampling to this to 60 frames, and also 16, sorry, and also all the segments are 75% overlap on each other. So that's how from the dataset they build all the inputs to train the model, their model. So that's the network architecture they use, which have five convolutional network, which are 3D convolutional, and at the end there are two fully connected, and the last one is a softmax in the first network, which classifies whether it's activity or background. It only has 2 neurons, and the other ones have the number of activities plus 1, which means the background. So that's a network architecture. That's how they train, and they train the whole network they fine-tune the whole network from the also the 3D convolutional part. They train it, and well, that's how I have talked about the nodes in the last layer. The localization network, as I have told before, they present a new loss function to add it. So they combine the loss function of the softmax, and also they added a loss function trying to compute the overlapping with the video notation. So, well, they ponderate it with a lambda. They get the best results with lambda equal to 1. So summing all the both losses, and well, you can see the loss of the softmax. Typically, we already know, and the last one is the overlap, which I'm talking to explain. They compute this loss when the true class label is predicted. Also, here in the calculus, here is the overlap for the segment with the true annotation, with the notation of the ground truth. Alpha is the sensitivity, and this is the probability predicted for that segment, and for each activity. So that's the way to compute it, and they get the best results with alpha approx 0.25. This loss function is stable with an alpha greater than 0.25 and less than 1. So that's it's stable. And here are plotting the loss against the probability predicted. So to have to take into context, the first one is a loss in the softmax. So if we increase the probability of prediction, the loss decreases. And here it would have it has been plotted for some values of overlapping. So if we have an overlapping, the segment has an 100% overlap with the ground truth, the loss behaves very, very close to as the softmax. But what happens if the overlapping is 0.5? Then it penalizes when the probability predicted is 1, because it is not really truly overlapping all the window. So it penalizes, and it tries to make that the probability predicted is more learning target, which is less. It's a less value. So that makes to penalize if there's the probability is low, of predicted or prediction is low, and also penalize if the intersection of a union is very low. Also penalize it. That's the mathematical demonstration that this loss function is differentiable and can be applied the gradients. So I'm not going to explain it. If you wanted to take a look. And then there's the prediction and post-processing they do after all. And on the proposal network, they keep all the segments which have a higher probability or higher than 70%. So all the remaining, they remove it as background segments. Also, they multiply the localization probability with class-specific frequency occurrence for each window to is to get the same, as he said, the same distribution patterns in window lengths. I haven't understood it too much why, but it seems to work. And then they do a non-maximal suppression based on the probability of localization. And here, this theta is the intersection over union probability. So they make a non-maximum suppression from this probability, well, this intersection, minus 0.1. So that's the way they do the post-processing. So let's talk about the experiments. To do it, they use two data sets. The first one, they only have two kind of videos. Videos with two different activities: bull chargescape and horse riding videos. Here's the information, and also the Thumus 2014. So the Thumus is an untrimmed videos dataset. So they offer videos which have activity located in it, and also and is used for action detection tasks. So has the results for the first data set, the MEX Action 2. So as you can see, the SCNN, the segment CNN, they achieve better results in both, in the bull chargescape activity most. On the second one, they get the same as the baseline, which is use dense trajectory features and plus an SVM. That's the results for Thumus dataset. It's misspelled the title. And here are the results. The first row is the intersection over union computed for that results. So as you can see, they achieve better results than the state of the art papers. And here are plotting the results on the Thumus dataset for some activities. You can see how they don't beat in all the activities, but in most of them. So you can see a little bit the global image, and that's the evaluation. For example, they make a prediction of this, and then they have multiple predictions. Some of them are removed because probably the prediction of location is not as high as they expect. And that's the way they work. So they try to keep it all the segments that have good prediction probability, and also thanks to the localization network, has the best intersection over union with the ground truth. So here are some examples. And also they have performed a study trying to remove the classification and the localization network and see the results. And as you can see, the results are better without the classification rather than with a localization. Localization network is what gives better improvements on this segment CNN. So that's the impact of the individual networks. And I don't know why the conclusions. Well, in general, the conclusions, they offer a new framework to detect and localize temporal activities in videos, adding a new network with a loss function, trying to penalize low intersection over union, and also making giving a lot of segments as proposing segments, and try to train the network. So they have achieved pretty good results. I like a lot this paper because I think it's quite interesting, and for the detection task is it's quite innovative the way they have tried to face the detection task. And well, that's all. If you have any questions, don't hesitate to ask.
Okay, thank you very much, Alberto.